Okay, before we dig into further into the stability descent method, we'll introduce several concepts about algorithms and convergence in general optimization problems. So when we talk about iterative algorithm, we mean that we're designing an algorithm, or this algorithm is trying to generate a sequence of points. We call them x0, x1, x2, such that hopefully this sequence will converge to the solution you want. Okay. Usually the x0 is the initial guess that is set by the user, and then the algorithm will generate the x1 based on x0, and then it will generate x2 based on x1, or possibly also based on x1 and x0 together, okay, so on and so forth. So in this case, you can see that we're obtaining a sequence, and in each iteration we get one iterate of one term in this sequence. So that's the in general, all the optimization methods are expressed as iterative algorithm. Okay, and we call a method descent algorithm or descent method if the sequence we generated using this algorithm satisfies this property. So that means starting from some initial guess, every time you move on to the new iteration, the new iterative generated will have a function value that is no larger than the previous function value. So say this is the xk is what you already have, and then you generate the next point xk plus 1, and you realize this function value is no larger than that. This method is called descent method. And this is a desired property for your algorithm, since we're trying to minimize the function f of x. So the goal is to find the point with the minimum function value. So if you can get this descent method to work, then the function value is at least decreasing. Not necessarily going to the minimum value, but at least decreasing. It's going towards a good direction. Okay. When we say global convergent, means that the algorithm will converge, not necessarily converging to global minimum, but at least it's convergent to some point, starting from any initial. Okay, so starting from any initial x0, the algorithm converges our generated sequence, which converges to some point. Then we say this method is globally convergent. Okay, and in contrast, a method is not globally convergent means that starting from some x0, the algorithm will converge. But if you give a very bad x0, the algorithm may not converge. Okay? That's global convergence. The local convergence is in contrast to global convergence. This means that if you have an initial guess that is sufficiently close to x star, or if you can generate a sequence such that the sequence generated by algorithm such that up to some point this xk is sufficiently close to the x star, then this algorithm will convert to x star. Okay, this is local convergence. So that means if you have, say, this is your x star. So if you start from very far away, maybe it will eventually go away. But if you have x star, if you start from x0, which is very close to x star, then it's always guaranteed to converge. So more formally speaking, this means that if you start x0 in the neighborhood of x star, so in the neighborhood it means that you have x star, and there exists a ball centered at x star with some radius. As long as your x0 is chosen from this ball, the sequence will always converge to x star. Then in this case, we call the method or the algorithm locally convergent. Okay. And also, we want the algorithm to converge, but we also want the convergence to be fast, so that the algorithm can be efficient to use. So what I mean here is that if you have algorithm that takes, say, 1,000 steps or 1,000 iterations to converge, then it is worse than an algorithm that can give you a convergence within 100 steps. So this difference in the convergence speed is formally called the rate of convergence. And we're going to talk about this soon later in this class, in this chapter. Okay, so now let's go back to the stability sim method applied to the quadratic function. So remember that a quadratic function can be always written in this standard form, where this term is a quadratic term, this is a linear term, Q and B are given. Q is a positive definite matrix, and the B is a given vector. Okay? So in this case, we showed earlier that the Hessian of this function f is just the Q matrix. And since Q is positive definite, we know the function is strictly convex, and it has only one unique minimizer. Okay? And so in this case, we know that there will be only one minimizer, and the function is convex, and there's no local minimizer. There's only one global minimizer. Okay? And also, because of the first order necessary condition, if x star is a minimizer of this function f, then the derivative of f at this, or the gradient of f at x star must be 0. Okay? Since we don't have any constraint, the first order necessary condition means that says that if a point is a local minimizer, then the gradient there must be 0. Okay? Now we only have one minimizer, x star, so the gradient must be 0 there. We show that the gradient of f is the gradient of this function f is just qx minus b. So when you plug in x star, you just get qx star minus b, which is equal to 0. Okay, so the x star is the global minimum, then qx star must satisfy this equation. And this equation is equivalent to this, right? And that also means that x star is the q inverse times b. Since q is positive definite matrix, the q inverse exists. Okay, so now let's consider that the convergence of the stability descent method. Remember that previously we have a closed form formula for the updated rule of stability descent algorithm. Let me briefly recall that. So remember that starting from any initial guess, the stability descent method applied to the quadratic function f can be written as this iterative scheme, or iterative algorithm, where this x is the current estimate you have. This gk is the gradient of f at xk. And since we have a quadratic function here, so the g of k is just gradient f at xk, which is just q times xk minus b. Right? So this is just the q xk minus b. Right? This is because f is a quadratic function. And similar for the others, they are just the same same gk. So use this formula to get the next iterate. Okay. So the reason of this is, as we showed earlier, this is stability descent method is one type of gradient descent method, which use the negative gradient as the descent direction and get a step size, the minimum step size along the line search function. And in the case of quadratic function, this minimum step size has a closed form, which we derived as this ratio. It's a scalar. This is a number divided by another number. So this must be so this is scalar, which represents the optimal step size. And now let's see what is the convergence behavior of this algorithm. Okay, to study the convergence, let's first define this following function v of x. Okay, the v of x for any given x, I'm going to define my v of x as the f of x plus a constant. Okay, so you can see that the vx is not much different from the f of x, but it's just perturbed by some constant. And this constant is a x star transpose qx star, okay, times 1/2. Remember that this is a constant, it doesn't depend on x. And also, you can do a very simple transformation of this fx, and adding these two together gives you this last line here. So let me show you that. So I have f of x so f of x plus 1/2 x star transpose q x star, and this is equal to 1/2 of x transpose qx minus bx, b transpose x. So this is the f part, and then I still have this part. This transpose qx star. Okay, and now let's see that this is my v. Okay, and let me check. So let's start out. This is my left hand side, and say this is my right hand side. This is my left hand side. So my right hand side equals to 1/2 of x minus x star transpose q of x minus x star. So I need to break the product. I will have 1/2 times, you can see that I'm going to have 4 terms coming out of this. It's like I'm breaking a square. Okay, so it's actually the x transpose qx minus 1/2 x star transpose qx minus 1/2 x star, x transpose qx star, and finally I will have 1/2 of x star transpose qx. Okay, and now I see that the first term, so the first term, this first term came from the product of this x and this x. Remember, there's always a q inside. And this term here is because of the product of its negative x star and this x. Similarly, this third term here is from this x and this negative x star. Okay, and the last term is just because of the negative x star and another negative x star. So I got that. Now I have the first term, which is matching the one I have. So this term is matching this. This term is matching this. So I only need to check if this one is equal to this. Okay, so let me work on this second term here. And first, the thing that you need to notice that these two terms are actually identical. The reason is you have x star transpose qs and x transpose q x star. These two terms are the same. The reason is you have the x star transpose qx. Remember that this can be written as q transpose x star transpose x, right? Because when you apply the transpose to q transpose x, we apply this transpose to the product of these two, then becomes the transpose on the first, and then right multiply by the transpose of this q transpose, which is q itself. So that's why this part is just equal to this part. Okay, and then this is equal to, say, now I have an inner product of two vectors. So one vector, I just treat this as one vector, this as another column vector. This is just the inner product of two column vectors. So it's the same if I switch their order. So we'll just have X transpose Q transpose X star. Okay, and remember that the Q is a symmetric positive definite matrix. We said it's positive definite, but as we said earlier, we always assume a positive definite matrix is symmetric in this class. So the Q transpose is just the Q itself. So that's why it's just X transpose Q X star. So that's why these two terms are actually the same. This is equal to this. And what it is equal to, it is just, you can pick up any one of them. Let's say this is equal to that. That's the two terms. And now let me check what this one is, for example. So as we said, this one is just Q X star, because Q transpose equals to Q. So this is Q X star. And remember that Q X star is the B from the previous page. Right? Q X star is the B. So I can replace this by B. So this is just essentially, this is the B transpose X. That means both of these two terms are just B transpose X. And I have two of them, and each of them is 1/2. So that's why this is just the B transpose X. And the last term does not change. Okay? And that's how we show that the left-hand side is equal to the right-hand side. Okay, so now you can see, because let me remove this. So now you can see the Vx is just this quantity here, and because Q is positive definite, so that means this quantity on the right hand side must be greater than or equal to 0, and it is equal to 0 if and only if this, remember these two are the same, this whole quantity is equal to 0 if and only if X minus X star is 0, and that also means X is equal to X star. Okay, so it seems that this Vx gives us a measure to evaluate how good this X is. It is always greater than or equal to 0, and it is equal to 0 only if and only if X equals X star. Okay, so to check how fast the algorithm converges, we just need to evaluate. We just need to see how fast this V of xk converges to 0, where this xk is the iterator generated by the algorithm, for example, the Stabilization algorithm. Okay, we just need to see how fast this one goes down to 0. Okay, to check that, we will first introduce this lemma, which says that if we apply the Stabilization method to generate the sequence in the algorithm we have showed the closed form earlier, this is the algorithm. We generate the xk plus 1 using xk in this way. Then it can be shown that the v of xk plus 1 is related to the v of xk in this form, where you can see that this is like a scaling of this v of xk by this quantity here. And this 1 minus gamma k is how much this scales. Okay, and hopefully you can imagine that we will want this 1 minus alpha k, gamma k to be between 0 and 1, because in that case the value here, which is positive number, will be scaled down, and the result we get will be closer to 0 than this v of xk. Okay, but we can show that when you apply Stabilization algorithm to this method, we'll get the gamma k here with this closed form expression. So this says that if the gradient is 0, then the gamma k will be just 0. And this is a trivial case, because if gradient is equal to 0, then remember that there is only one point that gradient is 0, which is the minimum value. So if you have g of gk, the norm of gk is equal to 0, or gk is 0, that just means that xk satisfies qxk minus b equals to 0, and that means the xk is already an optimal solution. Xk is the true solution x star. So that will be trivial. And in this case, your function value will not decrease anymore because this is already 0 and this is 1, but you still have just 0 here. Okay, and that can also be seen from the algorithm. If you have this xk to be the minimum value and the gk is 0, you can see this whole term is just gone. So xk plus 1 will be just identical to xk, which is already the minimum value. Okay, but in general, if the gk is non-zero, we haven't reached the minimum value yet, then this gamma k will be written in this form. Okay, it's a little bit complicated, but we will show this how we get this. And actually, there are only few important quantities. The alpha k is the step size. Okay, we'll express out what is alpha k because alpha k, we know the formula for alpha k. It's nothing but just this. Okay, but we keep this alpha k here just to give a general formulation for gamma k. And this is the inner product of gk and itself, so it's just a gk squared norm of gk. Okay, these two are the same. Okay, this is sometimes called, you see that it's the same as similar to this one, except there is a q in the middle. And what this one is, so usually we will have a vector x, and we multiply it by q and then x. This can be treated as we showed earlier, it can be treated as the inner product of these two vectors, x and the qx. And sometimes this is denoted by the q inner product. Which is how we define this one. So we define this to be this. Okay, and because this q is positive definite, symmetric positive definite, so this is actually a norm. So it's often denoted by the x q squared. Okay, means that's the q norm. A special case is that the q is just identity matrix. In that case, you can see this whole thing is just the square norm of x. Okay, if it's identity, then this is just identity matrix here, an identity, so you just have inner product of x with itself. In that case, it's just a standard norm. And similarly, we have this gk q inverse gk. So that's using the q inverse here, and also q inverse here. But remember that if q is positive definite, then q inverse is also positive definite. So that's why this will be kind of q inverse norm, squared q inverse norm of gk. But in either case, either of these two is, or both of them are positive. The reason is gk is non-zero, and q inverse are both positive definite. So this must be positive numbers. Also, these are positive numbers. Okay, so that's what the lemma says, and let's prove it. As we showed earlier, the gk, if the gk is 0, then we already reached the minimum. So the xk plus 1 will be just equal to xk, and the function value will be equal, and you already have the minimum function value. So in that case, our gamma k will be just 0. And what if the gk is non-zero? That means at the point xk, the gradient is still non-zero, and then we still have room to improve. And by the definition of v function, the v xk plus 1, we show that v of x is just the half of x minus x squared. Right? V of x is just the half of this, which is like as we introduced earlier, it's like the half of squared q norm of x minus x star. Right? So this whole thing here is just like 1/2 of x minus x star q norm squared. Okay, so we just recall that definition of v, or property of v. That would be just this, right? 1/2 of this distance transpose q times this vector distance itself. Okay, so now remember that the stability descent method is implemented in a way that the gk plus 1 is xk minus alpha k gk, where this alpha k, sorry, I should have the alpha k has a closed form before, right? So that's why this xk plus 1 is just this minus, let me see, it should be minus here, it should be minus here, and also minus here. So it should be this minus this, and also this minus this. Okay, and then we expand this product. We'll combine this. We put this together with this, and also sorry, we put this together and this together, and then we'll have 1/2. So let me show how this line is done. Let me show first that this is negative. This is negative. So how this is done? The 1/2. As I said, I put these two together, and then this. Okay. And similarly, I have these two together, and this one goes by itself. So when I expanded it, I should have 4 terms coming out, which are xk minus x star transpose q xk minus x star. So this was from the product of this q and this one itself. That's how I get the first term. Similarly, I get second term, which is minus 1/2 alpha k gk times transpose times q xk minus x, or minus x star. Okay, so this transpose is applied to this column vector and then gives us a row vector. And similarly, we'll have the third term, 1/2 of alpha 3 x minus x star minus, sorry, xk minus x star transpose q alpha k gk, and then finally we'll have 1/2 alpha k gk transpose q alpha k gk. Okay, and again, similar as before, these two are the same. This term and this term are the same, and they're together it's just equal to that. And this last term, you can see the alpha k can be extracted out because it's just a constant, and I will have the alpha k square, and then gk transpose q gk. That's the last term. And the first term, according to that definition of v, that's just this v of xk. So what I showed so far is that the value, or the v of xk plus 1, is just the v of xk minus this bunch of thing, or add this bunch of thing. So now, let's see, I take the difference. I know that this one will be eventually bigger than that. So I take a difference of this and this, I put down the numerator, and I divide it by vk. So now I know that vk plus 1, vxk plus 1 can be written as this thing. So this quantity here, I'll replace this one by this whole right hand side. And you can see that if I put this whole thing here to replace this, I'll see that the vk will be cancelled with this vk, and I won't have the minus this term left. So minus this term is the numerator I have right now. Okay, so now I reach to this conclusion. The vxk minus vxk plus 1 divided by vxk is just this. Okay. Now let's take a look at how to simplify the ratio, how to simplify this ratio. Okay, it looks complicated, but it will be simplified to very simple numbers. So first of all, we notice several things. The first thing is when we look at the qxk minus x star, xk is the kth iterate, x star is the minimum solution, the true solution. And remember the qx star is equal to b. Right, that's the property of the x star. Because it's a minimum, the gradient is equal to 0, so qx star must be equal to b. So that's why we can replace the qx star by b here. That will be just qxk minus b. But remember the qx minus b is just the gradient f at x. So that's why this is just the gradient f of xk. And by notation, by the definition over gk, that's just the gradient at xk. Okay, so this is simplified to that. And that is what we're going to substitute. When we see this term is just gk. Okay. Next, because this qxk minus x star is equal to g, so I apply the q inverse on both sides. The xk minus x star will be just the q inverse times gk. Right. So that's because we derived this from the previous line, the first line. Okay. Finally, because of this relation, when I look at the v of xk, I realize that this is the definition for v of xk. Right? And then I substitute the xk minus x star by that. So I will replace xk by x star by that, and also this xk minus x star by that. So what I will get here is, so this whole thing will be just 1/2 of q inverse gk transpose q times q inverse gk. And I know that this is just 1/2 of gk transpose. And the transpose of q inverse gives me the q inverse transpose. And then I have the q, I have another q inverse, and I have the gk. And now you can see that this q inverse are cancelled. So I only have 1/2 gk transpose q inverse transpose gk. But remember that q is symmetric. So the q inverse is just equal to the q inverse transpose. Right? Because q is symmetric. So the q inverse transpose is just equal to the q inverse. So this one is just the q inverse. And this becomes 1/2 gk q inverse gk. So I need to transpose on the first gk. So that's how we get this. Okay. And now we have all the simplifications that we need. We know how to represent this term, which is just gk. We know how to rewrite this term, and also we know how to rewrite this term. Okay. So as we said, if the first term is this here, this part is gk. So the gk with gk itself, inner product with gk itself, is gives me the square norm of gk. Right? So the whole thing here is just alpha k times the squared norm of gk. So that's what we define A to be the squared norm of gk, or the inner product of gk with itself. Then the first term just becomes alpha k times A. Okay. We also define the B to be gk transpose q gk. Okay. And then from this line here, the gk q gk, this part is just the B. So the second part I have on the numerator is minus 1/2 alpha k squared times B. So that's how I get this term. And the denominator, remember that we showed that this vxk is just this 1/2 gk q inverse gk. So let's define this quantity as c, then this denominator will be just 1/2 times c, right? Because vk is written as 1/2 times this, which is c. Okay, so now I have this formula here, and I make a very simple change. I multiply numerator and denominator by 2, also it doesn't change the value, and then I see that there is alpha k, common term alpha k here, so I extract it out, and also I extract this b over c. So c is common denominator for both of the terms, so I can extract it without problem. And also there's a b, so the first term doesn't have b, so I have to divide it by b. And the second term is just alpha k square times b, but b is moved out, the alpha k is moved out, and the 2, as we said, we multiply the 2 on both numerator and denominator. That's how we got to this point. And now you can see when I put this a, b, and c back, the a will be put back to this numerator. And remember that's gk transpose gk. Okay, and the b, I have these two both as b, so they will be replaced by that. Okay, so I'm going to replace the b by that, which is gk transpose q gk. The c here is the gk q inverse gk. So that's my c here. So it will be replaced by that. Okay, so now I have exactly the form I had earlier. I was trying to show. So this is alpha k. This is a b. This is another b. This is a a. This is a c. Okay, so you can see the match between the two. Okay, so this is how we finish the proof of the lemma. Okay, so because of that, we can see that every time we, for every iteration we do, the new iterate xk plus 1, or v of xk plus 1 will be equal to that, where this gamma k is what we just showed. Okay, and the gamma k is equal to 0 only if this xk is already minimum. Otherwise, it's the expression we proved earlier. Okay, so we can do this we can see this by iterations, because the vkx plus 1 is equal to 1 minus gamma k times vxk. And then we focus on the vxk here. So this should be equal to 1 minus gamma k minus 1 times v of xk minus 1. Right? So that combine these two together, we see that vkx plus 1 is just equal to 1 minus gamma k times 1 minus gamma k minus 1 times v of xk minus 1. And then I can further reduce this. This can be written as 1 minus gamma k minus 2 times v of xk minus 2. Right? You can keep doing that. Eventually, you will see that this index is getting smaller and smaller, and every time you reduce this index by 1, you extract one more term of 1 minus gamma something, right? 1 minus gamma. So you just keep decreasing this index here. Eventually, you will reach to v of x0, and when you get there, in the last step you extract a term 1 minus gamma 0 there as well. Okay. So in general, what we'll get is the v of xk. By doing this procedure, we can show that it's just the product of those 1 over gamma I. It's like 1 of gamma I, 1 of gamma k minus 1 times 1 minus gamma k minus 2 times 1 minus gamma k minus 3, all the way to 1 minus gamma 0. Okay, and then we have the v of x0 coming out here. All right, so now you can see our goal to show that the stabilization method makes this go into 0. So you throw in the initial guess, and you have some positive v here. And if you want to make sure this is going to 0 for k larger, you just need to make sure this product is getting closer to 0. It's tending to 0, right? For k goes to infinity, as k goes to infinity. Okay, so as I just mentioned, you want to show that this goes to 0, and that is if and only if this goes to 0, right? The sufficient necessary condition is that this goes to 0, and this goes to 0. Remember that when I take a logarithm, if this term goes to 0, then the logarithm of this will go to negative infinity. Right? Recall the plot of a log function. This is logarithm. This is the x. Let me show that. So this is the x. This is the log of x. So you can see that when x goes to 0, x means this whole thing here. X goes 0 means that the log of x goes to negative infinity. So the negative log of x, negative log of this will go to positive infinity, right? Negative log of this will become positive infinity. Okay, and here, from this step to this step, as we said, we apply the negative log on both sides. Okay, a negative log on this, we know that if you apply a negative log on this kind of thing, it will be just because log applied to the product will become sum of the log. That's how we get this. So that's how we get to this one, right? And this goes to positive infinity if and only if the sum of this gamma k goes to 0, goes to infinity. Only if and only if this goes to infinity. So this last step here needs more detail, as we show in the next slide. Okay, so why that is true? The reason is because if you look at the negative log, look at this quantity here, this is true for all the gamma greater than 0. Okay, the reason is so negative log let's say this is gamma, this is gamma, this is 2 gamma. Okay, and what I'm trying to claim here is that the negative log 1 minus gamma is actually in between. It's between these two. So this one is negative log 1 minus gamma. Okay, so why this? So we want to show that the sum of, remember that we're trying to show that the sum of this logarithm goes to infinity if and only if the sum of this gamma goes to infinity. So to show this, we can use the property of this one here for gamma greater than 0, but it's not sufficiently close to 0. Okay, so now here is the details. Say I have this is the claim that I want to make. I want to say that the sum here write this gamma k log of 1 minus gamma k is infinity if and only if the sum of gamma k is infinity. Okay, so we're assuming that this gamma k is between 0 and 1. The reason is that the 1 minus gamma k, you know that both sides are greater than or equal to 0. So 1 minus gamma k must be greater than 0. So the gamma k is less than 1, and also assume that gamma k is bigger than 0. If as long as this is true, then we can show that this series is infinity even only if this series is infinity. Okay, so to show this, let me first show this direction. Okay, suppose that the sum of gamma k is infinity. Okay, and then we can check the relation between, let me put a scratch paper here on the right. Let me compare the gamma and the negative 1 minus negative of log 1 minus gamma. Remember, the gamma is between 0 and 1. So let me compare this one. Which one is bigger? Which one is smaller for over the interval gamma between 0 and 1? Okay, so that's my question. Is this true for gamma? Okay, assuming that gamma is between 0 and 1. Okay, so to show that this is true, let's first define a function I call the h gamma. And I take the h gamma as the difference between the two sides. It's the gamma minus the right hand side, which gives me the positive log 1 minus gamma. Okay, so if I want to show this left hand side is smaller than the right hand side, I just need to show that their difference, which is h gamma here, is less than 0. I just need to show that this is less than 0. Okay, so how to show that the h gamma is less than 0 over this interval? Well, let's first see that h0 is equal to what? It's a 0 plus log of 1 minus 0, which is 0. And on the other hand, we can see that the h prime of gamma equals to 1 minus, remember that the 1 plus the derivative of log of 1 minus gamma. If you use the chain rule, that will be 1 minus gamma first, and then take the derivative of the gamma inside the log, which gives us a negative 1. And then combining these two, we'll get negative gamma 1 minus gamma. And now you can see when gamma is between 0 and 1, the numerator is negative, the denominator is positive, right? So that's why this denominator is always greater than equal to 0. Negative, less than equal to 0. Okay, over the interval this. So if I draw the picture of h gamma, that means it starts from 0. The h gamma is 0 when gamma is 0, as we showed here. And then the derivative of h is negative. So that means starting from 0, the h gamma will go down, right? Because the derivative is negative, so it's always going down. And that shows that the h of gamma will be less than or equal to 0. Okay, and h gamma less than or equal to 0 means this is less than or equal to 0. That means this gamma is less than or equal to this. Okay, so only gamma equals to 0, then you have these two are equal. But when gamma is less than 0, then you have a strict less than equal to gamma is strictly less than negative log. Okay, but doesn't matter. We can keep this less than or equal to notation, the inequality here, and we can get that the sum of log 1 minus gamma k is infinity. Okay, and the reason is just because what we showed here, that for gamma between 0 and 1, this is actually true. Okay, so you take the sum of gamma k, and on the right hand side you also take the sum of gamma k. So that's how we show that the sum of gamma k is infinity, and this one will be only bigger than this, right? This quantity here is even bigger than this, so it will be also positive infinity. So that's one direction. To show this direction, So suppose that right now we know this sum is infinity, and we want to show that this is infinity. Okay? So if not, let's prove it by contradiction. If not, then the sum of gamma k will be this, right? Will be bounded. And this means that the gamma k needs to go to 0, right? Otherwise, this infinite series will blow up. Okay, it has to, at least it has to go to 0. Each gamma k has to go to 0. While gamma k goes to 0, then I only would need to worry about the behavior of gamma k near the near 0. Okay, I know that is between 0 to 1, and I know that the gamma k will be very close to 0 for sufficiently large case. Okay, so now I'm going to do something similar to what I wrote on the right. I'll show that the negative log 1 minus gamma is less than 2 gamma. Okay, and to show this, I'm going to use the same trick. I define my h gamma as 2 gamma, which is the right hand side, minus the left hand side, which is log of 1 minus gamma. Okay, now you can see that when I plug in 0, then I have 0 plus log of 1 minus 0, which gives me 0. On the other hand, h prime of gamma, I take the gradient, I take a derivative with respect to gamma, I will have 2, similar to before, it's negative 1 over 1 minus gamma. And when I combine the two, I will have 1 minus gamma on the denominator, and on the numerator I have 2 minus 2 gamma minus 1, which is 1 minus 2 gamma. Okay, so remember now that I know this, I'm going to see that the gamma, I'm going to substitute the gamma by gamma k. I'll see that the gamma k is approaching 0. So for k is sufficiently large, gamma k is definitely close to 0. Say it's between 0 and 1/2. So it's between 0 and 1/2 means that this is positive, and this is also positive. So that means my gamma k, my h prime of gamma will be positive for, say, gamma between 1/2 and 0. And now what we get is, so this is gamma. I know that when gamma is equal to 0, the h gamma is 0. So it's starting from the origin, and the derivative is positive. Right? At least up to 1/2, the derivative is still positive. So that means it's still growing. And it's growing means that h of gamma is positive over this interval. And that means this is positive over that interval. Okay, and that means this is a, sorry, again, that's the equal to. So if this is a positive, as we said, if this is greater than or equal to 0, and this quantity h gamma is just the right hand side minus the left hand side. Okay, so we can move this to the right hand side and it will prove this line here. Okay, so that's why when hk, this means hk goes to 0, and since 2 times sum of gamma k, k from 1 to infinity, is bigger than 2 times sum, say negative 2 times sum of k from 1 to infinity log 1 minus gamma k. Okay, this is because when I substitute this gamma by gamma k, then I should have this sum of this bounded to bound this sum of this side. Okay, you may ask that what if that at the beginning of the time when k is not that large, the gamma k, we do not have this relation, means that the gamma k is larger than 1/2, in which case we do not have this greater than 0. Well, if there's only, but remember that this doesn't matter, because we know that the sum of this less than is bounded, means that the gamma k will go to 0 eventually. So starting from some k, this gamma k will be between 1/2, 0 and 1/2. So what happens at the beginning, say it will be a very big k, and up to that big k, this will be close to 0, or it's between 0 and 1/2. So we just ignore that, the first terms. We can say this is the big K, say this is the big K, say K is 100 terms, or 200 terms. So after 200 terms, I will have all my gamma K between 0 and 1/2, and then I should have this as well. But the point right now is that if I know that this sum here gives me an infinity, right, that the infinity is given by the infinite sum. If I only have finite sum, say I remove the first k terms, first capital K terms, it does not, it's just still finite many terms, so it will not affect, it will not make this one blow up. What can make this one blow up is the infinite sum for k from big K to capital K to infinity. That is how we made this right hand side positive infinity. But on the left hand side, even if you take the sum, partial sum from capital K to infinity, this should blow up. And that is a contradiction to our hypothesis here. And that's why this cannot really happen. The infinite sum here must be infinity. Okay, see, let me repeat what I'm saying here. So now we're trying to show this direction. We're trying to show that if the sum of infinite sum of gamma K, or the series of gamma K, is infinity, then the series of this must be infinity as well. And the reason is, if not, if this, we're trying to show this direction. So we want to show that this is infinity implies that this is infinity. And what we're doing here is that if this right hand side is not infinity, but the left hand side is infinity, and what happens is that the right hand side is infinity implies that starting from some capital K, this gamma K will be close to 0. Say it's between 0 and 1/2. And according to our relation here, each of this gamma K will be bigger than or equal to the negative log of 1 minus gamma K here. Okay, that's why the sum of this over the K's will be bigger than or equal to the sum of this for all the K's. Okay, and this will bound, this 2 of this will bound this. Okay, sorry, I shouldn't have the 2 there, just this. Okay, so that means this will be bigger than this. And according to our condition, we know that this is infinity. So that means this must be infinity as well. Okay, and that is a contradiction to this. Okay, so here is a contradiction. So that's why this right-hand side also implies the left-hand side. And now, once these two are proved, we can see from this page that this v of xk goes to 0 if and only if this infinite sum goes to infinity for k going to infinity. Okay, so the series should go to infinity. And that's the conclusion that we make here. The theorem says that if you have a sequence xk that's generated by gradient algorithm, it doesn't have to be the steep descent algorithm. It's just a general gradient descent algorithm, which is written as xk plus 1 equals to xk minus alpha k gk. When you apply this algorithm to the quadratic function here, then the iterates we get, the xk we get, will convert to x star if and only if the sum of those gamma k's is infinity. Okay, this is how we prove the general result. So this result is pretty, actually it's pretty special. It considers the gradient descent type of algorithms. And it tells us a sufficient necessary condition for this algorithm to converge when the objective function is a quadratic function. Okay, so that's the claim we are making here. Okay, so now let's check what happens if we use the steep descent algorithm. In that case, we know what is. In that case, we have a specific choice of this gamma k, alpha k, which is the step size in the steep descent method. So to study that, we will need this Realist inequality to derive a estimate for that step size alpha k. Okay, so Rayleigh inequality is regarding the properties of the symmetric matrix Q. So remember that our Q is positive, symmetric positive definite matrix, and a property of this Q is that the X transpose QX. We have been using this a lot, right? This is the quadratic term in the quadratic function. This term, we said earlier that this is you can treat it as a squared norm of Q, and this quantity is bounded between the two values. One value is the norm of X squared, standard norm of X squared, and this is the smallest eigenvalue of Q, and this is the largest eigenvalue of Q. Okay, so suppose your Q, since it's symmetric, let me write it. It's a symmetric positive definite. I know there exists a eigenvalue decomposition of this matrix, and the eigenvalue decomposition gives me this. Okay, let me put the transpose here, and this U, I know that is orthonormal, right? It's orthonormal matrix. U transpose is just the transpose of U, which is also the inverse. Okay, so U transpose equals to U inverse. Okay, and the lambda is a diagonal matrix with the eigenvalues of Q on the diagonals. It's like lambda 1, lambda 2, all the way to lambda n. So let's say that we sorted these eigenvalues in a descending order. The lambda 1 is the largest one. Lambda n is the smallest one. So you could have some repeated ones in between. For example, lambda 2 could be equal to lambda 1, but I'm putting them in descending order. So this is like the lambda max of Q. This is a lambda mean of Q. Okay, so what I'm claiming here is that if you take a look at the X transpose QX, it will be bounded by this lambda mean of Q times the square norm of X, and lambda max of Q times the square norm of X. Okay, so the reason of this is you can see. Let me show you why this is true. So I'm checked X transpose QX. Well, for any X, I write this X transpose QX, but remember the Q has this eigenvalue decomposition on the left, which is U transpose lambda U. So this should be X transpose U transpose lambda U X. Okay, so now I treat this UX as Y. Okay, and this one here will be just UX transpose, which is a Y transpose. So the whole thing here is just a Y transpose lambda Y. All right, so now say the Y is this vector y1 through yn, and then I will have the y1 yn, lambda 1 lambda n, it's diagonal, and then I have the y1 through yn. Okay, so let's see what happens when I multiply these three together. It's very easy to show that it's just a lambda 1 y1 squared plus lambda 2 y2 squared all the way to lambda n yn squared. So apparently, since we have a symmetric positive definite matrix, I know this lambda are sorted from lambda 1 in descending order from lambda 1 to lambda n. And since it's positive definite, I know that all the eigenvalues are positive. Okay, it's just lambda 1 is the largest positive number here, and lambda n is the smallest one here. So that means on the one side, this quantity here is bigger than or equal to the lambda n y1 squared plus lambda n y2 squared plus all the way to lambda n yn squared, because lambda I is greater than or equal to lambda n. So each of them is bigger than equal to lambda. So that means lambda 1 is bigger than lambda n lambda 2 bigger than or equal to lambda n, all the way lambda n bigger than equal to lambda n. Okay, and similarly, you can show that this quantity here is less than or equal to lambda 1 y1 squared, lambda 1 y2 squared, all the way to lambda 1 yn squared, right? This is because lambda 1 is the largest one among those lambdas. Okay, so let's just say that on the one side I have this, and this, since they all have this lambda n, I will have just lambda n times y1 squared all the way to yn squared. Okay, and this is equal to lambda n. According to the definition of norms, this is just the y norm squared. Okay, so what I showed here is that this x transpose qx is bigger than or equal to lambda n y squared. And what I really want to get is this x transpose qx is bigger than lambda n. Remember, lambda mean is just lambda n times the y squared. The only difference is that here I have the y squared, x squared, and here I have the y squared. But these two are actually the same because of the property of the orthonormal matrix U. Recall that I call this Ux to be Y, right? And the U is orthonormal matrix, means that actually you know that if it's orthonormal matrix, means it's just kind of rotation or reflection. So it doesn't really scale X anyway. So the length of X should be the same. You can also see this from here. So let's say I have the Y transpose Y. This is the X. Sorry, this is the Y norm. Right? It's just Y, inner product of Y and itself. And remember that the Y is Ux. So I have this X, Ux transpose times Ux. And I put the transpose on each of U and X. I have X transpose U transpose Ux. But since U is orthonormal, so this is just identity. Okay, and that's why this is just X transpose X, and that is just X norm squared. So that's how. That's why this is essentially just the lambda n x squared. Okay, that shows the left-hand side here, and similarly as we said earlier, this can be less than equal to. This should be less than equal to lambda 1. All these things are lambda 1 here. Then you can show that this is less than equal to lambda max times x squared. Okay, all right. So that's the Rayleigh inequality. It tells you that this Q norm, squared Q norm of x, is bounded between the standard norm of x times the lambda mean and the lambda max of Q. Okay. Another property of this Q or the Q inverse is we have the eigenvalue decomposition of Q with this as the eigenvalues, then we can also get the eigenvalues of the Q inverse. The reason is for very obvious reason, since we have the Q equal to this, so the Q inverse will be equal to the inverse of Q, U lambda U inverse. And then you know that you have the inverse of the product, that will be just the product of the inverse with the reverse order. So I first need to apply the inverse to the last U. So I have a U inverse, and then I have the lambda inverse, and then I have the U transpose inverse. But remember, U transpose is U inverse. And take a inverse again, that still gives you the U. And remember that this U inverse, the first U inverse is actually U transpose. So I just get a eigenvalue decomposition of Q inverse. And you can see that the middle lambda inverse is just, this lambda inverse is just this 1 over lambda 1 through 1 over lambda n. Okay? And you know that they are all positive numbers, since all the lambda are positive numbers. But the only thing changed here is that the lambda 1 used to be the largest one. It's the largest one. So 1 minus lambda 1 becomes the smallest one. So right now the diagonal entries are sorted in an ascending way. So this is the smallest one. This is the largest one. But anyway, it's still an eigenvalue decomposition. And now you can see the smallest eigenvalue of Q inverse is 1 over lambda 1, which is 1 over the largest eigenvalue of Q. So that's where this one comes from. Right? This is the smallest eigenvalue of Q inverse is 1 over the largest eigenvalue of Q. And similarly, the largest eigenvalue of Q inverse is the smallest one, 1 over smallest eigenvalue of Q, which is this. Okay, based on what we just showed, there will be a very easy way to get the following inequality. The lemma says that if the Q is a symmetric positive definite, then for any vector x, we have this ratio bounded between these two numbers. Okay, so this left-hand side is like lambda n over lambda 1. This right-hand side is lambda 1 over lambda n. Okay, and this is very easy to show build on since we already have the Realist inequality. So we factorize this this one here into two parts. So to do that, let's first recall the Realist inequality. The Rayleigh inequality says that the squared Q norm of x is bounded between these two. Right? That's the first the Realist inequality. What the Realist inequality says exactly the one here. And on the other hand, if I replace the Q by Q inverse, then the Q inverse of the square Q inverse norm of x will be bounded between the square norm of x times the smallest or minimum eigenvalue of Q. But the minimum eigenvalue of Q, as we showed earlier, minimum value of Q inverse. We showed earlier that this is just equal to that. Okay, so we showed this. So that's why this 1 over this lambda max of Q is just the smallest eigenvalue of Q inverse. Okay, and this 1 over this is just the largest eigenvalue of Q inverse. So just applying the Rayleigh's inequality to the case with Q inverse, and recall the relation between the eigenvalues of Q inverse and Q, we'll get this. Okay, so according to this two, the first one implies that if I divide all the sides by this number here, then I will show that this divided by this will be less than or equal to 1 divided by this. Okay, so you can look at this. You just make a simple algebraic change, you get that. Okay, and similarly, this part, if I divide both sides by the squared Q norm of x and the lambda max of Q, I will get this. Okay, so that's why the ratio here is between the 1 over lambda max of Q and the 1 over minimum value of Q. And similarly, we do this. We look at this. So on this side, if I divide both sides by the squared Q inverse norm of x, and then I will have this. Right? Just move this to here and this back to here. So it's a very simple algebraic change. And similarly for this part, when I divide both sides by the squared norm of Q inverse of x, squared Q inverse norm of x, and multiply both sides by the lambda mean of Q, I will have this. Okay, so now I factorize this into two of them. It's just a product of that and that. So they multiply together gives me this quantity. So that's why it must be bounded between the product of their own lower bound, which gives me this, and they should be bounded above by their own upper bounds, which gives me this. Right? Okay, so that's how we show this inequality.